Hey everyone, welcome back to the channel. In this video, I'm going to show you how to modify the output of an SMPS power supply, allowing you to increase or decrease the output voltage. We have a 12-volt 6-amp power supply here, and in this video, I'll be showing you how to convert it to a 24-volt output. Let's connect it to the mains voltage and check the output. As we can see, there is 12 volts at the output. Let's open the case and identify the parts. There is a safety fuse. Here are the internal parts of this power supply. This is the mains input terminal, which is connected to the safety fuse. The output from the fuse is connected to the MOV. MOV is connected across the main input line after the fuse, to protect the circuit from overvoltage. This is an NTC thermistor here, which stands for negative temperature coefficient, is connected in series with the circuit. When the temperature increases, the resistance of the NTC decreases. This is an X capacitor, which acts as a low impedance path for high-frequency differential noise, shunting it away from the power supply circuitry, and preventing it from being conducted back onto the AC mains. They are connected directly across the AC input lines. An EMI filter coil, used in electromagnetic interference filters, which is used to block high-frequency noise while allowing the desired lower frequency signals. Another EMI filter coil and X capacitor. Bridge rectifier. DC filter capacitors, used to convert main AC voltage into DC. Snubber network, which is used to suppress voltage spikes and oscillations. And a LED indicator. This is the power MOSFET, which is mounted on a heatsink to dissipate heat, which is used to drive this ferrite transformer. This is the PWM IC for this power supply, which generate high-frequency clock signal, between the range of 40 kHz to 130 kHz. This signal is used to drive the gate of the power MOSFET. Here is the block diagram of this IC. These are the startup resistors, which provide initial voltage to the PWM IC when turn the power supply on, which is connected from main filter capacitor to VCC pin. This is the auxiliary winding of the transformer. The output from the auxiliary winding is also connected to the VDD pin of the IC, through a rectifier diode. The initial power is usually supplied through startup resistors connected to the high-voltage DC bus. Once the switching starts, the auxiliary winding generates a voltage that is rectified and filtered to power the controller. This is the feedback IC, which keeps the output voltage stable. It helps regulate the output voltage by controlling the switching of the power transistor through an optocoupler. It is a TL431 programmable voltage shunt reference, commonly found at the output of the power supplies. This is the schematic diagram of a standard TL431 IC. Here, pin number 3 is the cathode. We take the output from this pin, which is connected to the positive supply through a resistor. Pin number 2 is the anode, which is connected to ground. Pin number 1 is the reference pin, where a voltage divider network is connected to control the output voltage. The output voltage, Vout, can be calculated using the following formula. It is usually available in a 292 package with 3 pins, which is a standard shunt regulator. However, in this power supply, it comes in an SOIC 8 package, with 8 pins, and it has an extra features, such as improved stability or lower noise. Now let's check the datasheet of this IC. According to the datasheet, pin number 1 is the cathode, pins 2, 3, 6, and 7 are the anodes, and pin number 8 is the reference. This is the secondary output, which is rectified by a Schottky diode. Smoothing capacitors are used to filter the DC voltage, and an inductor is also used to smooth the output current and keep the output more stable. Here is the output terminals. Let's put the fuse back into the fuse holder. Before we make any changes to the power supply, let's measure some voltages. Here we can see a green indicator. Let's measure the main input voltage. The input voltage is 265 volts DC. And the output is exactly 12 volts DC. Let's measure the VCC voltage, which comes from the auxiliary winding of the transformer. The VCC voltage is 16 volts DC. In many SMPS topologies, the TL431 is used in the secondary side feedback loop to regulate and maintain a stable output voltage. It monitors the output voltage via a resistor divider network. By changing the values of this voltage divider, we can adjust the output voltage accordingly. As we discussed, to change the output voltage, we need to adjust the values of the voltage divider connected to the reference pin of the shunt regulator. In this case, this is pin number 8. We can see that there is a track connected to pin number 8, which leads to these SMD resistors. We can also see some other SMD resistors in this area, so we need to check them with a multimeter to identify which ones are used to generate the reference voltage. This resistor is connected to the reference pin from the positive terminal, and these two resistors are in parallel and connected to the reference pin from the negative terminal. Before we make any changes to this power supply, we need to check the values and voltage ratings of the capacitors used in it. At the beginning of this video, I mentioned that this is a 12-volt power supply and that I'm going to convert it into a 24-volt one, so we need to check the voltage ratings of the capacitors to ensure that they are within the acceptable range. Mainly, we need to check the values of two capacitors. One is the VCC capacitor, and the other is the output capacitor. Let's check the VCC capacitor. Its voltage range is up to 50 volts. Now we have to check the datasheet of the PWM IC to find its voltage rating. Here, we can see that the maximum voltage we can apply is up to 32 volts. If we increase the voltage beyond this value, it can damage the IC. The VCC capacitor has a voltage rating of 50 volts, so we can say that it is within the acceptable voltage range. Now let's check the output capacitors. They have a voltage rating of 25 volts. Since our target output voltage is 24 volts, these capacitors are not suitable, as they don't provide a sufficient safety margin. So we have to replace these capacitors. I am going to use this 35-volt capacitors in place of the current ones. As we discussed before, I am going to replace this 12 kilo ohm resistor with a variable resistor to change the output voltage. This is a 25 kilo ohm variable resistor. I'm going to use it in place of the 12 kilo ohm resistor. Here, I connected this variable resistor in place of that SMD resistor. And I'll set it to 12 kilo ohms to match the original value. Now let's turn on the power supply. We can see that the green output indicator is on. We have 12 volt at the output. I hooked up the multimeter to the output. Now let's rotate the variable resistor. We can see the output voltage changes as I turn the resistor. I can increase the voltage up to 13 volts and decrease it down to 3 volts. Beyond 13 volts, the PWM-IC goes into shutdown mode. I've set the output voltage to 13 volts. Now we need to check the VCC voltage of the PWM-IC. As I mentioned before, the auxiliary winding voltage also increases when we raise the output voltage. Here, we can see the VCC voltage has increased to 19 volts. Before it was 16 volts. So, we need to set the voltage within the safe operating range. As we saw earlier, the output voltage cannot be increased beyond 13 volts. To solve this issue, we need to check the datasheet of the PWM-IC. If we check the datasheet, we can see the OVP pin, which is pin number 7. It stands for over voltage protection. The OVP pin on an SMPS controller IC is used to monitor the output voltage and shut down or protect the circuit if the voltage goes too high. In this circuit, a voltage divider network is connected to the VCC pin to generate the OVP threshold voltage. In the datasheet, we can see that the minimum value for OVP is -1 volt and the maximum value is 6 volts. In this circuit, this is the auxiliary winding. From the auxiliary winding, we can see a resistor connected to a diode. The output from the diode is connected to OVP pin of the IC. There is another resistor which is connected from OVP pin to ground. These two resistors form a voltage divider to generate the VOP threshold voltage. Now, let's measure the OVP voltage. It is around 21 millivolts. Now, I am going to replace one of the voltage divider resistors with a variable resistor to adjust the OVP threshold voltage. Before we connect the variable resistor, we need to add a voltage regulator at the VCC pin of the PWM IC to keep the VCC voltage within a fixed range. To do that, I'm going to use this transistor-based voltage regulator circuit. I already assembled the circuit, let me show you how it works. Here, I connected a 24-volt power supply as the input voltage. And at the output, we get 14 volts. Let's solder the voltage regulator onto the PCB. I am going to cut the track here, which is connected to the VCC pin. Now we can connect the variable resistor to adjust the OVP threshold voltage. Here, I've made all the necessary connections to adjust the output voltage. Now, let's connect the power supply to the mains input and see if we can increase the output voltage. The output voltage is 12 volts. Let's check the VCC voltage. It's 14 volts. Before, we couldn't increase the voltage beyond 13 volts, but now we can raise it above 13 volts by adjusting the VOP threshold voltage. We can see that the output voltage has increased up to 16 volts. Let's measure the VCC voltage once more to see if there are any changes. There are no changes in the VCC voltage, it's still showing 14 volts. Let's go ahead and increase the voltage. At 17 volts, the IC entered shutdown mode. Let's adjust the OVP voltage. We have to adjust the OVP voltage until we reach our target output voltage. I could increase the voltage only up to 21 volts because the variable resistor has reached its endpoint. If we want to increase it further, we need to add an additional resistor in series with the variable resistor to increase its resistance. Here, I am going to connect this 4.7 kilo ohm resistor in series with the variable resistor to increase its resistance value. I've connected the resistor. Now let's turn on the power. We have 18 volts at the output, let's increase the voltage gradually. We're getting about 25 volts at the output. Let's set it to 24 volts. Now we have our expected voltage at the output. Let's turn off the power supply and then turn it back on to check if there are any issues. There are no issues with the output, it's working well. Now we need to set the OVP threshold voltage by adjusting the variable resistor connected to the OVP pin. Once we adjust the variable resistor, we need to turn the power supply off and on to check if the output is stable. We need to keep adjusting the variable resistor until the output becomes stable. Now we have stable voltage at the output. Now we have to measure the values of these two resistors by removing them from the PCB. Then, we will replace the variable resistors with fixed value resistors. The total value of this resistor is 27 kiloohms. Let's measure the other resistor. Its value is 15 kiloohms. Let's replace these two variable resistors with fixed resistors of the same value. I have soldered the resistors. Now, let's check the output voltage. The output voltage is slightly lower than before due to the resistor's tolerance. However, we are getting 23.97 volts. Now, let's remove the voltage regulator from the PCB and resolder it properly, so we can close the cover. Since our target voltage is slightly lower than before, I am going to replace one of these resistors to increase its resistance value. Here, I have another resistor with the same value. Let's install this resistor and check if there are any changes at the output. Now, let's measure the output voltage. We have exactly 24 volts at the output. That's all in this video, we'll see you in my next video. If you like the video, please subscribe to my channel.